Hello, welcome to this webinar presented by SmartEye. My name is Aaron Galbraith and I will be your host today. First off, we would like to thank all of our attendees for joining the webinar today. We hope that you'll find this webinar useful in understanding how head and eye tracking are helpful for aviation research. Do note that questions may be asked at any time during the presentation via the Q&A section. All questions will be queued until the end of the presentation, and then we'll take the time to answer a few of them live for you. So please stick around and enjoy the presentation. Next, I would like to get into some introductions. Again, my name is Aaron Galbraith. I'm the sales engineer for North America. I will be moderating the webinar. There will be 3 members from SmartEye speaking during this presentation. All 3 members work for the Research Instruments division of SmartEye. First up, we have Mr. Brant Hayes, North American Sales Director. Next, we have Mr. Ulf Lufberg, Sales Director for Europe and APAC. Next, we have Mr. Sebastian Johansson, Sales Engineer for Europe and APAC. Okay, so I will now hand the presentation to Mr. Brant Hayes, who will explain in more detail the purpose of this webinar.
Hi, thanks, Aaron. Yes, so eye tracking has been used for years in various types of human factor studies within the aviation sector, whether it's psychological or physiological type studies. In recent years, there has even been an increase in the demand within the aviation sector and even more an acceptance and use of eye tracking in other types of use cases as well, such as design and validation, and even in training. There are several methods of eye tracking available on the marketplace. The purpose of this webinar is to focus primarily on the remote method of eye tracking, specifically the 3D multi-camera SmartEye Pro system. We'll be discussing the unique features that contribute to the successful use of this technology as cited in several aviation use cases, and also how the flexibility of this system allows us to take a unique approach to each individual case. So here's an agenda of today's webinar, and just for a quick rundown, we will be discussing the difference with the differences you'll experience with the remote method of eye tracking. We're going to highlight several successful use cases with this technology, and finally, we'll discuss the SmartEye approach and provide a brief demonstration for you, which focuses on the unique features. So I'll be taking us through the first part of the agenda, which will be to define 3D remote eye tracking and discuss the unique features of the multi-camera SmartEye Pro system. So as a brief introduction to remote eye tracking and what differentiates this method from the others on the marketplace, the main objective is to create a non-intrusive environment and to really encourage naturalistic behavior with the participants during the experiment. The fact that there's no headgear or any other wearable devices allows for free movement of the subject, as well as the ability to test other wearables as well as the ability to test with other wearables such as helmets, with or without microphones or even visors. The cameras are actually placed in the environment and they're configurable and customizable to the application. By using a world coordinate system, we're able to output all fields of data, both head and eyes, in 3D. We do this by measuring everything from one static point of origin, and we are able to replicate any application environment in a 3D world model, which this is a unique feature of the SmartEye Pro, and we'll discuss this later on in the demonstration portion of the webinar. This allows for much enhanced accuracy, as it really simplifies the data collection and how we present the data for post-process analysis. The SmartEye Pro is also unique in the fact that among the eye trackers, remote eye trackers in the marketplace, that is, it's the only solution that can expand past 2 cameras. We can actually go up to 8 cameras, and the flexibility and the scalability with the system allows for relatively free placement of the cameras and to either add or remove cameras to suit multiple different types of application environments. So just to highlight some of the unique features of SmartEye Pro, we begin with the small form factor or the footprint of the hardware that is used in the application, which we will demonstrate later. These can easily be integrated or even embedded in the application. Again, the scalability and flexibility of the multi-camera solution allows for customization of the system and to configure to any application while still meeting field of view requirements and also while still remaining optimal accuracy. All fields of data and the objects measured and presented in the 3D world model are measured from a static point of origin, which really helps simplifying the data output. And finally, the robustness of the multi-camera system allows for the naturalistic behavior and movement by the subject. Cameras can even be occluded during the experiment as the other cameras are still tracking. And this allows for very minimal data loss and gives us the ability to output very reliable and accurate data. So the relevant data fields, basically our data output can be broken down into 6 categories. I like to comment on each in terms of the difference that can be experienced with a 3D multi-camera system. The 3D capabilities allow us to provide 6 degrees of freedom with the head, or basically head, pitch, and roll. A much greater freedom of movement can be experienced with the multi-camera system. With the gaze direction, we have a 3D vector and can track the gaze direction and origin of each eye or binocular, as well as the consensus vector. The gaze intersection, by using the 3D world model, we can output 2D intersection points, as well as pixel coordinates on both items or subregions on the objects in our 3D world. With the eyelid opening, we have many data points on both the upper and the lower eyelid. And this really allows us to measure the state of the eye, whether it's actually opened or closed, as well as open and closed speeds, and even blinks. With the pupillometry module, we output the diameter of the pupil and can detect the pupil dilation, which is commonly used in cognitive studies when determining stress and workload. And finally, we have an analysis portion, which there are customizable filtering options to determine fixations and saccades. And just to reiterate that with the exception of the analysis piece, all of the fields of data are output in real time. So with that, I'm going to pass this on to my colleague Ulf Lufberg for the next section of today's webinar. Thank you.
Thanks, Brent. So I will now run you through 8 different use cases of customers deploying the SmartEye Pro solution. These are studies involving research on human performance, health and physiological factors, HMI design, human factors, and pilot training. The trackers were used to investigate topics like workload, pilot cooperation, drowsiness, disorientation, design and validation, and pilot performance comparisons. This first use case is from the Swedish Civil Aviation Authority, LFV, in cooperation with Linköping University, and addresses workload experienced by remote tower and remote pilot operators. Remote tower means that the ATC operator is not physically located at the airport directing aircraft. Remote piloting means that the pilot is not physically located on board the vessel, or a ship, if you will. A 5-camera SmartEye Pro system was deployed to investigate and optimize processes around human-centered automation. The eye tracker detects visual behavior while the operator is gathering and processing digitized information presented on multiple screens and monitors. The purpose is to enable an instructor to understand the gaze and scan patterns executed by the operator, and thereby make sure the information is presented in an optimum way on the screens. To secure all gaze data is recorded and presented without delay, 4 main technical characteristics have to be fulfilled by the tracker. Precision tracking over a large area, tracking on multiple screens and monitors, high data availability, and live data forwarding, or real-time data transmission onto a network. Here is a use case on human performance, which is done by the University of the German Armed Forces and addresses workload in the cockpit. The study group has designed a system that uses eye tracking data, speech, and flight control inputs to estimate the current activity and workload of the crew. As a second step, an adaptive associate system, or you could say an artificial crew member, uses the rated workload information to automatically support the crew in optimizing their activity and to mitigate high workload. To make sure that the eye tracker captures the necessary gaze data, also for this customer, it was important to deploy a high-performance tracker that provides a large field of view, high data availability, and live data forwarding. In addition, the tracker must be able to gather synchronized data from multiple pilots. The university is working with several 4-camera Smart Eye Pro systems in both fixed wing and rotary wing simulators. Here is a case from the US Naval Medical Research Unit. The unit recently inaugurated what is mentioned as a new generation simulator, enabling next-level realism to motion simulations. The so-called Kraken simulator is helping researchers gain a more complete understanding of motion-related factors in various moving vehicles. For the first time in the history of aerospace medicine, fully realistic motion simulations can be created, which allow the exhaustive research necessary for a comprehensive understanding of spatial disorientation and other motion and acceleration-based phenomenon. Accurate evaluation of issues like spatial disorientation, operational effectiveness, and performance and safety are investigated. The main reasons why the research unit is using Smart Eye Pro is freedom to move for the pilot or the driver, a modular setup of the tracker, so you can choose different frame rates. You can choose, as Brandt mentioned before, the number of cameras you need for this particular study, and also the number of IR flashes. Further reasons are also all the different data options available in Smart Eye Pro, in the software Smart Eye Pro. And last but not least, the ability to provide and maintain during all the movement accurate head and eye measurements under extreme simulated movements and high gravitational forces. The next two cases describe projects where Smart Eye Pro is used for HMI design and validation, as well as human factor studies. So the left case of this slide, or the left side of the slide, is from the NASA Neil Armstrong Flight Center in California. Eye tracking is used to help the workstation design through analysis of workload and drowsiness. The target is accurate gaze tracking, head tracking, and eyelid movement tracking across 4 screens. The case on the right-hand side is from the Federal Aviation Administration Next Generation Integration and Evaluation Capability Lab in Atlantic City. Smart Eye Pro is deployed in air traffic control simulators to test and validate new functions developed for the ATC user interface. Precision gaze tracking is required, but the measurements have to be equally accurate across several screens. The FAA also requires remote trackers. The latter, again, to avoid unwanted influence on the study results from using a wearable tracking device. The last 3 use cases describe the deployment of Smart Eye Pro in flight simulators with the aim to apply eye tracking to the pilot training process. The main question here is, does the use of eye tracking enhance the quality and efficiency of pilot training? The eye tracker provides the instructor with 2 advantages. A, the instant knowledge of what the pilot is currently looking at, and B, the ability to record the pilot gaze behavior and later on show it to the pilot. In these studies, recording and analysis tools were designed to capture pilot gaze behavior during different flight maneuvers. Part of these solutions are video recordings with scene cameras, as well as visualizations and statistics of the pilot gaze and scan pattern. Eye tracking data was then put in relation to actual flight control inputs and aircraft flight data. All voice, tracking and input data and other parameters are synchronized and presented in real time to the instructor during the flight session in the simulator. The same data is recorded to be replayed during the post-flight debriefing together with the pilot. On the current slide, we see tools created by Isae Supaero at the University of Toulouse in France. It was important for the team to use a remote system with a wide field of view that provides accurate gaze tracking data with superior data availability. To present gaze data to the instructor in real time, the head tracker must also cater for live data forwarding. A research group with Thales AVS outside of Paris has developed a prototype called Humans. Also, Humans can be used as a pilot training system and is depending on the Smart Eye Pro to provide eye tracking data. Successful trials were done in helicopter flight simulators. Helicopter pilots operate with an even broader field of view compared to commercial aircraft pilots. Therefore, Thales deployed a 5-camera Smart Eye Pro system. On the picture in the middle of the slide, you can see real-time view displayed on a tablet held by the instructor during the flying session. On the lower left picture, you can see a snapshot of the debriefing tool, where the pilot and instructor go through the session together by replaying the contents and zooming in on certain events. David Rudy at ETH in Zurich, together with Swiss Lufthansa and NASA, conducted a similar kind of study, as well using Smart Eye Pro in the flight simulator cockpit. Also, this group designed a solution aimed at helping flight instructors, and they call it Eye Assist. A 3-camera Smart Eye Pro system was used here to gather gaze data. Additional research groups around the world have been doing similar studies, creating prototype systems to help the instructor to better understand under which circumstances a particular pilot has sufficient knowledge, ability, and skills, and for what other parts of the training the pilot needs more exercises. Using eye tracking to support the flight instructor is definitely not a new topic. Based on recent activities on this subject and the number of software prototypes available today for training, we do believe that a commercial deployment of these systems, so-called evidence-based training systems, on a broader basis is imminent. It's a very interesting development, and we want to talk more about that, but at this point, it will not fit into this webinar, so this is something we will come back to at a later stage. So that concludes the section of our 8 use cases. I now hand it over to Sebastian and a demonstration in the cockpit.
Thank you, Ulf. Now we've reached the point of the webinar where we are going to discuss the Smart Eye approach and also take a look at a demonstration in our in-house flight sim. So we start by really gaining an understanding of the project and the goals of the research. That includes understanding requirements in terms of what field of view is required, as well as accuracy and any objects of interest. We also need to understand what limitations could have an impact on this and may need some workaround. That could be things like limited camera and flash placement. The pilots could be wearing helmets or with visors, and there could be IR interference in the room. We then customize a solution with a customized number of cameras and placement according to these findings, and present the solution and expectations in terms of field of view, accuracy, etc. for approval prior to installation. So with all that in mind, let's head over to our in-house flight sim for a live demo.
So let's take what we just talked about and really put that into practice. We start off by going to discussions with the customer to really understand the project. And this particular use case is design and validation, looking at workload and stress levels, as well as gaze distribution over time between the interior of the cockpit and the exterior during takeoff and landing scenarios. The customer wants to compare and aggregate data of at least 30 pilots doing at least 3 runs each, so that they can either confirm the current configuration or suggest a new cockpit configuration. We were given some requirements. The interior, especially the area with the main instruments, need really high accuracy. The outside view doesn't need as high accuracy, but we still want to be able to capture gaze on all of the 3 monitors. So we are talking about quite a wide field of view. The customer wanted a remote system with minimum setup time. and they may occasionally be wearing headphones with microphones. And they really want a non-intrusive system, which is why they prefer to embed the system to really strive for naturalistic behavior from the pilots. There are also some limitations to take into account. There could be conflicting IR sources within the room. They did not want to wear any headgear in terms of eye tracking system. And again, the hardware cannot interfere in any way with the instruments or operation of the yoke. So to come up with a customized solution, we start off by building a replica in-house to test and determine how many cameras and illuminators are needed to achieve this, as well as the position of the cameras and illuminators. We come up with a final configuration when we decide that that actually meets the requirements from the customer. And then we go back to another discussion with the customer to really present our conclusions and expectations. Are there any areas that they couldn't meet the requirements? And what are the expectations that we can deliver on in terms of accuracy in their desired areas? Once we have a sign-off from the customer and approval, we're then ready to send a final proposal. So looking at the actual installation, it really comes down to two parts, hardware and software. If we start off by the hardware, in this case, we chose to embed a 3-camera DX system. So we have 3 cameras embedded here, as well as 2 illuminators, 1 on each side. But even if the customer hadn't chosen to embed the system, the footprint of the DX camera is still small enough to be able to hide in plain sight. When we have all the hardware set up and installed, we're ready to go on to the software. So we use a 3D laser measurement tool to really measure all of the objects that the customer wants to collect data on, from the larger instruments on the side to the screens in the center, and we can even create sub-regions if we want to as well. We do that using this 3D laser measurement tool that really gives us absolute coordinates on all of this. So that allows us to create an exact replica of this cockpit in the software. So now I'm actually ready to bring in my first test subject. So I'm going to have my colleague Brant come in and sit down. And as he sits down, even though I realize you may not be able to see it very well, but we are going to take a look at this in the software as well. But I would still like to point your attention to the bottom right of the screen, where you can really see that 3D replica of the cockpit. And as he's gazing around, you will later see all the gaze intersections and all that on these objects. I would also like to point your attention to the 3 camera views for each camera. That really displays the freedom of movement that he has. And even though he may cover a camera occasionally, the other cameras will still be able to capture him to really make sure that we have minimal data loss. So now we're ready to jump into the software and really take a look at all the capabilities and features that are in the Smart Eye Pro software.
So let's start by taking a look at the head box, which is what we call the area that the participant can move around freely within and still be tracked. The system automatically captures landmarks on the head, which are represented by these white dots. The landmarks are then used to automatically build the 3D head model, which is used to calculate head position and rotation within the 3D world coordinate system. You can see the origin of this head coordinate system being displayed here at the center of the head. The position of the eyes are then brought from the head tracking, and using corneal reflections coming from the IR illuminators, we're able to calculate the gaze direction. And even though a camera might from time to time be covered, the system is still robust enough to maintain tracking to really make sure that there is minimal data loss. Now, if we head over to the 3D world model, we can again see that this is an exact replica of the cockpit measured using our 3D laser tool. When first setting up the software, we decide on a point of origin for our 3D coordinate system, in this case being placed here. This point can be based on a number of known things, such as the position of a camera or the chessboard, and it can be offset as well to match another coordinate system, giving you the capability to collect data from multiple systems using the same point of origin. We can also see representations of the cameras, as well as flashes, and the head of the participant, and also the individual gaze vectors per eye.
Being the fact that all the data is in 3D relative to this known point of origin, and using a static world model like this, it really simplifies and speeds up the post-processing of the data. And you can see as the subject is gazing around on the different objects in the world model, how they light up, and intersection points are being calculated, letting you know not only on which, but precisely where on each object the subject is gazing. This data is then found in the intersection category and will be using the labels of each of these objects. So if we head over to the live data stream, we can here see the labels of each object being gazed at, along with the local coordinates on that object, as well as the global 3D coordinates of the intersection point as well. As you can see, there are multiple data lines in each category, all including data per eye, as well as unfiltered and filtered data. There are also quality indicators for most of these parameters. To be able to access and post-process this data, all you have to do is really choose where you want the data to go. You can either send it on a UDP or TCP stream, or simply save it as a CSV text file. You can add multiple UDP and TCP streams, choosing different categories to be sent on different streams. Now let's take a look at the data in Excel. So looking at the data here, we can see that all of these parameters are timestamped. In this case, we have 60 data lines per second since it's a 60 Hz system. And looking through the log file, you can really see how accessible the data is. And should you want to take a look at this log file yourself, replay the webinar, or request an on-site or online demo, just head to our website for more information. Now I'm going to be handing this back over to Aaron, who will wrap up the webinar.
All right, thank you, gentlemen. There have been a couple of questions so far. So at this point, oops, we want to get into the question and answer time. So, please use the Q&A interface inside of the live event. We'll be able to field your questions. As I mentioned, there have been a few questions so far. Please bear with me one moment while I take a look through them and select a few of them to discuss. In the meantime, please use the Q&A section if you have any questions. Okay, let's start with this question first. So it says, it may not be easy to find space in the cockpit to mount cameras. What are the options for using fewer cameras, and how does doing so affect the performance of the eye tracking?
I can take that one, Aaron.
Okay.
Right, so if you don't find enough space for a camera, what do you do and what does it cost, so to say? As Brand mentioned, the system can work with either one camera or up to 8 cameras. You use more cameras when you want to have a wider field of view. You need that when the pilot is turning the head to the side, for example. You also would like to maybe concentrate 2 cameras closer to each other to achieve a higher accuracy of the gaze measurement. So by reducing the number of cameras, the trade-off would simply be to either reduce the field of view or reduce the accuracy of the gaze measurement slightly.
Okay, thanks, Wolf. We got another question here. It says, how do you deal with interfering IR sources?
I can take that one. So what we do both when we have interfering IR sources that are already present in the cockpit, as well as when we have multiple Smart Eye Pro systems, to make sure that these systems does not interfere with each other, is basically starting by looking at the wavelength of the light. Our light operates at 850 nanometers, so unless if we are in different wavelengths, then we have nothing to worry about basically. But if we are, then our synchronization box that basically triggers and both the cameras and the illuminators, we're able to either send that trigger signal for another system to desynchronize from ours, or receive a trigger signal so that we can desynchronize our system from the other system. Since our exposure time and the time that the illuminators are on is very short, there's plenty of time that we can desynchronize to.
Okay, thank you. Excuse me. During the presentation, you mentioned that the points being tracked on the face are important. What would happen if the pilots wear a face mask covering some of those points up?
Actually, I don't mind answering that one as well. So as I mentioned in the beginning of the software demo, we do rely on these landmarks to be tracked to be able to calculate the head position, and from that the gaze as well. However, the system is redundant enough so we don't need to track all these points on the head at the same time. So you are able to cover some of these, specifically, wearing face masks, and the mic can cover some as well. But as long as we still have some of these landmarks to track, it works very well.
Okay. Next question we have, when classifying fixations, what time or dispersion criteria are used and how were those selected?
I don't mind taking that one as well, actually. So there are some settings in the software on how to classify fixations. You can classify how many degrees per second of gaze movement that is allowed, and how long you need to dwell on the point as well. But you can also look at the raw data from the data stream and classify fixations yourself as well, if you should prefer that.
Okay. All right, so I see, can you elaborate on what may be involved with the setup in between participants?
Yeah, I can take that one, Aaron. Yes, so I mean, going in between one participant to another it's very automated and quite simple. Again, there's no wearables in the cameras, they're static in the environment. So really, it's just a matter of taking a seat and getting started. It's that simple. So as Sebastian went through the head model and the demonstration with the face model dots and everything, the profile of the participant is generated and then obtained pretty much instantly, a matter of seconds. So there is a gaze calibration that is still needed to be performed to ensure that you do get the highest level of accuracy, which literally this takes about 30 seconds. You can then save the profile and the calibration results to load for future runs. So, and then it's just really a matter of clicking the track button to begin tracking. So really, all in all, the process can be as short as a couple of minutes if needed.
Okay. Next question I have is, I was interested in the gaze quality measure and how this might be used as a threshold to determine whether to include or discard data points. Can somebody speak to that?
Sure, I can speak to that, Aaron. So it's not really that easy of a question to answer, since the quality measures rely on a number of different things. It's basically depending on how well we're able to identify things such as the pupil. We define that as an ellipse, and basically trying to match all these data points to the pupil. So it has to do with a lot of different things, as well as we mentioned that the system uses not only the IR light to illuminate the image, but also the reflection of the IR light on bouncing off the cornea. So that also has to do with it, how well we can detect those points, and so on. So there are thresholds to look at, and it can really be helpful as an indication of how much you can trust the data points. but how it's calculated is not a quick and simple answer, really.
Okay. I have another question then. How do you calibrate or validate the digital construction of the real world environment? I believe that's a reference to the 3D world model.
Yeah, I don't mind picking that one up as well. So as we mentioned, we use this laser chessboard tool, and the way it works is really the software and the cameras, they track the position and the rotation of the chessboard, and then there's a laser distance meter that provides the distance from the chessboard to the point that we're measuring. And we can measure a number of different points. The measurements themselves are very precise, and they use a separate software from Smart Eye Pro, and we can verify that by taking multiple measures, and then when we verify the gaze, we can not only calibrate on these points but also verify the gaze position on these points as well.
Okay, last question we have. How static does the participant have to be in order to complete a gaze calibration?
Let me take that one as well. You don't have to be very static when doing the gaze calibration itself. We normally encourage naturalistic behavior. So, if you need to move your head or, in any other way move in order to get a naturalistic look on that point, then that's perfectly fine as well. What is important is to focus on the points and especially don't blink during the collection of those points. But the sampling of the gaze when doing this calibration is very short. I believe it's about 0.5 or 0.7 of a second that we collect. So you don't have to stare at these points for very long.
Okay. And with that, I think we'll end the Q&A session. So do keep in mind that we have some upcoming webinars. Please stay tuned to our webpage, emails, and other social media for information on our upcoming webinars. In the near future, we do have a few planned. The next one that is planned will be in December, and this is using head and eye tracking for automotive HMI research and development. Thank you once again for attending this Smart Eye Research Instrument webinar. We have more webinars planned. We'd love to see you there. Bye for now.